And I'm going to be taking pictures of the class as attendance, so we don't have to go around and take an individual attendance, but if something happens and they do contact tracing, I can just look at the picture and figure out who was attendance and where they were sitting, so if someone has COVID, we can trace that threat. Honestly, with the 6 feet, the regulations pretty much are, even if someone next to you got it, you probably don't have to quarantine as long as we have masks on, which everyone does. Thank you. And we're 6 feet apart, which everyone is. Thank you. The projects are all going to build on each other. The labs kind of build up. They're pretty good labs. Not everything is going to be in lecture. Some of what you'll need to know, do the reading is what I'm saying. Read the book. If it's assigned reading, read the book. It's not too bad. There's a section here about unannounced quizzes. That hasn't been done. I'm not doing unannounced quizzes this semester, even though it's in the syllabus, because if you catch COVID, I don't want you feeling like you have to come in. I want you to feel like you can stay home, watch the video, send me some emails to make sure everything's okay, and move on. You're not going to miss a quiz. If you're going to miss a final exam or something, we'll figure it out. Like, there's some of these growing pains as we figure out this whole pandemic thing, but my goal is to not make it painful for you guys. There is a link to the student expectations for this semester that are a little bit special due to COVID, and there's a little digital addendum link that's on there as well. Both those things that you should read. It's mostly about COVID and what will happen if we have to go online. If you are new and you need some sort of disability or accommodations, reach out to the accommodations office. What do they call it here? I have a link in this one. Student Services for Students with Disabilities is in room 181 of the Student Services Center. So reach out to them and they'll work out if that means more time for exams and various other issues. They can help you work through that. And I will work with them again to make sure that this semester is as unpainful as possible considering the state of the world. One of the ones that I like to point out, if we end up going on Zoom and you're at home on your laptop, don't take the laptop into the bathroom with you when you take a break, because people keep forgetting to turn off their cameras when they do that. I do mean keep repeatedly doing that, and it's very embarrassing for everyone. Just don't take your laptop into the bathroom. You can miss a couple of minutes. You'll be okay. There is a lab book guideline on that. We'll get into, we have the lab later today. Which I'll talk about actually a little bit in this class. This sheet, the lab book guidelines, kind of tells you how to make it and then shows you how to make it, which I think is really more useful than anything. The reason we do this is because this is actually expected in industry. Because if you create something for your company and then someone else is like, no, we have that patent, then you can go and show that, no, look, we have this work before you did. And it's about copyright protection, intellectual property protection, all of that stuff. And the way we do it is the way you're supposed to. So like in industry, your lab notebook is property of the company and needs to be such that you can't add something to it without leaving evidence. So like so you can't have a 3-ring binder, because the issue with the 3-ring binder is you could then write your name on it, sign a date, and then insert it in a 3-ring binder. And look, I discovered this 6 years ago, right? That's not admissible evidence in court. So your companies will be happy if you follow the guidelines. Any questions on the syllabus, on who I am, on what we're doing here? Yeah.
The book, is it only available in the...
Yeah, it is. Yeah, yes.
Oh, were you gonna...
Yeah, no, that's all there is. Sometimes I like ramble.
I'm sorry. Ask about the breadboard and like the other supplies needed for the class.
Yes.
I have my own breadboard and stuff.
That's fine.
I should use that.
Yep. Yeah, there's nothing special about the breadboards in the bookstore or anything. So if you have your own stuff, your own wiring kit, we in general will supply most of the electronics for it. And I think what I'm going to try and do, we'll see if it's not too much work, is I'm going to create little packets of electronics for you so that we don't have to be congregating. Because normally we just have like them laid out. But due to COVID, we don't want like big groups of people in one spot. So I'm going to try and create little packets to hand out to everyone that hopefully you'll hand back the electronics if you don't fry them. Cross your fingers. People break electronics all the time. It happens. It's forgivable. Other questions? Okay. A lot of people are new to electricity, or what they have is from physics, so I'm going to kind of start at the beginning so we all have at least some shared understanding of this. So electricity we talk about in terms of volts and amps, right? Electricity can really be, there's some good metaphors between water and electricity. A volt is like stored energy. It's like a big bucket of water sitting at the top of somewhere. A volt can just sit there and do nothing. But if you hook up a pipe to it and it flows, that flow is what we call current. In water and electricity, it's the same thing. We have symbols that we'll use for circuits that are very common. I might go to erase this, office hours. It's also posted on my door. And my email is on the syllabus. Let me make sure I didn't typo that. I'm a little crazy these days. But so the first symbol is what we'll call a voltage source. And you'll write something like 5 volts next to it. Yes?
So just to keep my notes like organized, is this like section 1 of like?
Yes.
In like section 1 of 1 or like?
Yeah, this will be section 1 of the book.
Okay.
It may not correlate 100%, but I will try and keep it that way. The book is Fawn Browns, who's another faculty member here. He wrote it. I am going to stick to that so that if he teaches the next section, there's some continuity there. But yeah, this is all. Today will be chapter 1, pretty much. Yeah, I'm pretty sure I think I'll get all the way through chapter 1 today. This is what we call a voltage source. This could be as simple as a battery, where this is the negative terminal, and that's the positive terminal. And that would mean it raises 5 volts. Now, a volt is kind of a little bit of an abstract idea. And so if we look back, electricity is charge, right? Which is electrons. And we define it in terms of coulombs. This is how we define charge. Coulomb. C-O-U-L-O-M-B. Coulomb. And a coulomb is just the charge that results from you're not going to see that. Times 10 T. That's a 6, not a G. I have terrible handwriting. I will try and make it legible. If it's not, yell at me. 1 coulomb is that many, the charge that results from that many protons. And a volt is explicitly, like, this is not the scientific definition, but it is how much work a coulomb of positive charge will do to get back to the negative charge. And what that really means is, if I put 5 volts up here, it really wants to get back down to here. There's no path right now, right? This is what we call an open circuit. And we would usually draw that like this. Now, for a battery to do anything, it has to be connected, because a volt is relative to something. There's no such thing as like absolute 0 volts. So most of the time, we do it to what we reference as ground. Drawn like so. In this building, ground literally means they've taken a metal rod, driven it into the ground, and that's what the negative polarity, the ground wire, so if you look at a socket, and it has this guy, that's actually literally connected to earth ground. It's because Earth is big and it's very good at absorbing charge. Other things that are absorbing charge, big plates of metal. If you look at something like this, it doesn't connect to earth ground. Its ground is board ground, which is just a sheet of metal that runs through the whole thing in the middle of it. In short, your electricity needs somewhere to go. Now we have components of electricity. Sorry, do you have a question? Okay. Which is the most basic is a resistor. That's the symbol for a resistor. A resistor means it's difficult for electricity to go through. In terms of water, it's like a low resistance is a big pipe, and a large resistance is a small pipe. So if it's flowing through a big pipe and then suddenly hits a small pipe, you're going to get a backflow of water, right? Because it can't flow through that as freely. And that's where we get to Ohm's law. Where the volts is a result of current, I, multiplied by the resistance. So if I hook up this circuit, the unit of resistance is ohms. I use the omega symbol, 5 ohms. So we can solve for the current going through there using Ohm's law, where the current is equal to the voltage, which is 5, divided by the resistance, which is 5, which is equal to 1 amp. 1 amp is a lot of electricity. 1 amp would hurt. Other important components for us, actually, I don't know if they are. I'm going to try and keep this simple. You'll learn a lot more in 1270, I believe, is the course number for the analog stuff. But we just need enough. Other important components for us is a switch, which we will draw like this. This is an open switch. No electricity flows between an open circuit. When it closes, then electricity shows. You'll also see it with an arrow through it, like so, sometimes. One of the weird things that happened is Ben Franklin, in the early days of electricity, knew that electricity flowed, but they didn't have particle measurement systems. It was very new, right? So he had to take a guess, essentially, at what was causing electricity to flow. And his guess that it was positive charge, and he was wrong. But we've stuck with his notation this whole time. So positive current, 5 volts going to ground, positive number, is actually the opposite direction of the electrons. So negatively charged electrons flow in the opposite direction of what we call positive current. All because Ben Franklin guessed wrong. It's a reasonable guess, right? I mean, it's positive, positive. He was thinking in terms of protons, but that's not really what does the work here, unfortunately. Yeah. So, we have electricity. We have the basic components. When we want to do stuff with circuits, most of us in this course, we're not power engineers. We're not dealing with what we call DC power. We're dealing with AC. And a lot of what that means is signals. What's a signal? Anyone? If we're talking electronics, what's a signal?
Low or high voltage. Like
what's the point of signal? What do we do with a signal?
Transmit information.
Yeah.
Yeah, we transmit information. And that's a lot that's a lot of what we try and do with digital electronics, is the transmission and manipulation of information. And so we have 2 different kinds of signals, really, that we are concerned with. Okay, if I erase this. One of them would be like FM radio. Continuous time analog signal. But your computer doesn't think analog. It doesn't. This has an infinite number of voltage levels, right? You can go in and measure time scale. It might be 1 volt up here and -1 volt down here. Perfectly loud signal goes along. You can pick any time and it might be 0.000001 volts. In digital, that's what we're working with. It's what we call sampled, meaning that it has a resolution. And it can only tell the difference at some finite amount. So what that means is, instead of this continuous time analog signal, your digital signals are going to be like, okay, I see a dot here, see a dot here, and it raises up. And they're going to be equally spaced in time because you're on a clock, a system clock that goes tick, 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 and takes these samples. And if it's, say, in the middle, say it takes a sample here, and the next, I'm going to exaggerate this, is up there, it has to choose which value it's closest to. So this is going to be here. So your sinusoid, sine wave, sinusoid, is going to look like a series of dots that you can imagine do this, but it's not there. So that's what digital signals look like, is they have definitive voltage levels, step functions. They're not continuous. And that's what we'll be concerned with. Oh, I missed one electric signal. Yeah, we'll get to that later. It's fine. Does everybody get the digitization, that general idea? Okay, so in digital, we have a couple of different ideas of standards that we'll use for digital communication. In the book, there's a table that talks about the 3 major ones that we're concerned with, which is TTL, CMOS, and ECL. And really, TTL and CMOS are going to be most of what you do. And what these do is they're just standards. Like CMOS could be, well, we could pull it up. So TTL could be between like 2 and 5 volts for high voltage TTL. Usually you'll see it at like 3.3 or 5 volts. And what that's doing is the numbers are all represented with 1s or 0s, right? We've all at least heard of the idea of binary data. Again, that's 5 volts, 0 volts. We would call this a 1 and this a 0. Now say something weird happens and I sample a voltage here at 2.5 volts. What does it do? It guesses, right? It has no idea what that value is. And in reality, these systems actually have memory, which is interesting, where if it's been high and it's going low, and I sample, as long as I'm above about here, it'll count as a high. Because it takes more energy to flip to the 0 than it does to stay at a 1. Then the opposite is true. If I try going from a 0 to a 1, I then have to get over this. This is useful because real systems have noise, so it's not going to be nice and flat like that. It's going to be like that. Because you have a digital system I'm working on here, and really all of the data transmitting from your guys' phones that you're secretly texting on the thing is interfering with this signal. Now this is much more powerful because you're having to radiate to it, but that can happen. So you want to try and design some of your design is making sure that you don't do weird sampling points. Because we're in a clocked system a lot of times for communication. And the ideal situation is that you're taking that point. If you miss that by a little bit, you're wrong. And we're going to build some systems that do this later on in this semester. CMOS, we will get into. That's the other most common. CMOS comes from transistors, which are everywhere. They're in your phone, they're in your process, every processor, all of that. Now, knowing they're there is good, but we have to measure them, right? So we have a couple different tools to measure them. One of them, and I do highly recommend buying your own, they are not very expensive, is a voltmeter. This is actually what we call a multimeter because it can measure multiple things. The way it works is if I'm trying to measure DC voltage, right? Steady state voltage, not changing. I change it to the DC voltage range. It will have two leads that plug into here, which I don't have. And you'll touch each of the lead to two parts of the system and take a measurement. The reason you need two leads is, again, volts is not absolute. So the ground in this building could be different from the ground in the next building because it might be charge in the ground. So what that means is you need a reference. So one of them is a reference, one of them is what the voltage is. So you touch one to ground and one to the place you're measuring. That's a voltmeter. The next is an oscilloscope, which we will see in the lab later. And this is a useful tool for measuring signals that change over time. It's a waveform viewer is what it will look like. And so we call this a waveform, and analog can be a waveform. You go in, measure it, and it'll show you a movie of what the electricity is doing, essentially. The other one is logic analyzers. Logic analyzers are digital-only things that often are designed to plug into up to 200 or more digital channels. And that's really to evaluate complex digital systems. And then there's also a logic probe, which is literally it just lights up and tells you if it's a 1 and it's off if it's a 0. Again, relative to reference. So, in order to do these digital signals, we have to make these digital signals. And that's really what Lab 1 is about, is how to make digital signals, which we'll get into more detail. But if we use these symbols that we know, I have a power supply, and I have some digital out that I want. I can simply install two switches. If I close this switch, what's the digital value? 0. If I close that switch, it's a 1. Of whatever this voltage is, right? Now there's a danger is if you're building this with like manual switches, as we will, what happens if they're both closed? Should I say louder?
You do a continuous feedback loop?
Kind of. It's less about feedback and more about Ohm's law.
No resistance.
Exactly. So what is the current?
Infinity.
Infinity. So this is like taking a 9-volt battery, taking a wire and touching it to both ends. That wire is going to heat up very quickly and melt your fingers off. Don't do that because your board, whatever you're using as a power supply, whether it's a battery or a power supply on a bench, cannot provide infinite current and you might break it. Fortunately, the bench power supplies, they have protections against those these days, which is useful. But if you end up with a digital system and you do that, this is a $150 board. If I do that to it, it will break the board. At least part of the board usually. New systems, they're great. When I was a student, they didn't have this. Now when you break it, you only break part of the board. It's really great. You used to break the whole thing. Don't recommend doing it. Yes. So the way we do this in practice is we can do physical switches, click, 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 right? That's like what this has. This has a whole row of switches. And they can be used to turn on lights and things on the board. If you tell it to, you have to program it, which we learned to do. Or we can use nice new transistor technology. This has been around since like the 50s, but the two main that we're interested in, well, the main one, we call them Mosfets. This is the simplest way to draw them. Make sure I'm not going to do anything fun. Source, gate, source, drain. So, G is for gate, D is for drain, S is for source. We're not going to worry too much about how these things work. For the purposes of digital, and this is why analog designers will often make fun of digital designers, is these guys really are nothing more than switches, where this is a switch that closes. Closing means it switches on, so a closed switch is on. Closes when the gate voltage is high. So if the gate goes high, the drain connects to the source. PMOS is the opposite. If it goes low, the switch is closed. So we can replace these switches with those gates. Now it's useful to have this. We call it CMOS, right? Term you heard? C in CMOS just means complementary. And that's a useful thing to have. I should specify. Anytime there's a wire, we call that a node, N-O-D-E. And the node, it can do crazy things, like it can connect to a resistor up here, and then like a capacitor over here or something. That node is always at the same voltage. It's a wire. Wires have zero resistance. That stops being true, but for small digital systems, it's effectively true. So, what you do, so here's a new symbol. This is a power symbol. We often note the positive power supply as VCC. You will also see me, because I'm a bad student, just write V plus next to it as the power supply. And this is your input. This input is going to come from some other part of your system. And it's either going to be a 1 or a 0. So with what I just said about the NMOS and PMOS, if this is a 0, the 0 comes in here. What is D out? 1, exactly, yes. Why is that?
Because the PMOS gate will be closed, letting it flow through, and the closest one is a D out and not the ground.
Yeah. And what's nice is that this, in this case, only one of these can ever be closed. So I flip it to a 1, and so like this one is turned on, and the output is ground, because this is open. You can't break this type of system. It's great. but it has a problem. It's what we call an inverter, right? If I give it a 0, it outputs a 1. How do I make something like this as a not inverter? If I put in a 1, I want a 1 out.
You switch which Mosfet connects to ground and which to.
Yeah, so, trick question. It sounds like you could just switch them. Unfortunately, due to characteristics that you'll get into in later classes, they actually don't turn on if you do that. So you're stuck with an inverter. The way you do it if you don't want an inverter is you stick two of them together. You invert then invert. That's the way you do it. Like, there are more complicated ways to do it and less efficient ways to do it, and we'll actually do a less efficient way of doing it for our lab. But I'll get into that in a moment. Yes, okay. So, we now have a simple digital circuit. It has some digital output. And it feeds into some digital system. So a lot of times we'll have what we call a block diagram, which is where we'll just write a block. And then we'll connect up power. The same way, like that. So this power can be used in multiple places. It's like taking multiple wires from the battery and plugging it into all the systems you need, which is useful because if you have one running off of 3.3 volt logic and one running off 5 volt logic, they won't communicate very well. So this is really how we draw a lot of our systems. All right, that actually went very quickly. Do we have any questions so far? So I'll take a... Yes?
So going back to where you said you can't actually flip those MOSFETs to make it be a 1 in and 1 out.
Yeah.
What was the reasoning why you can't do that?
You'll get into like deep details of it, but ultimately it's because these have to satisfy a set of equations and be able to turn on. Which in this case, the voltage at the gate has to be greater than the voltage at the drain in order for, plus another factor. So if the NMOS is up here, when the gate is a 1, that's the same as this VCC, right? And then your V gate, the gate voltage is equal to the drain voltage, and it's still not on.
So it has something to do with the actual like transistor, like.
Yeah, it's the device physics is what we call the subcategory. Yeah, so I want you to be aware that the device physics exists, but it's not within the scope of this course to teach it to you. When I did my education, we actually did digital logic. This course was a 3rd-year course. So you built up a lot of the analog device. So there's some discontinuity between how you're going to learn it and how I learned it. And I'm just trying to make sure that we have limitations with the digital logic. I don't expect you to know why you can't do that, but I do expect you to know that you have to do that. Other questions? Okay, so I'm going to talk about the lab so we can get a little bit of a jump start on that and flow through it quickly today, which is 1:30, I believe. The lab will be online if it isn't already. You can print it out there. Lab breakdown is pretty much why we're doing the lab, what you need for the lab, and what you need to do prep. Prep for this one is essentially nothing. A lot of times I would do the lab the 2nd week, but I really want to get it started on as quickly as we can because of the COVID situation. So this one uses what I called earlier a bad way of doing this. So it just is using a switch. If the switch is open, what's the output? 1. This is what we call a pull-up resistor. So unless the logic is doing something, it is pulled up to 1. When the switch closes, it gets pulled to 0, and there's no resistance here. So that means this whole thing becomes 0 volts. VCC tries and pulls it up, but the resistor blocks it from doing what it's supposed to. And so a current will flow through here. So you need to pick this resistor. We'll show you how. To be a right value, because if it's a 1 ohm resistor, and this is 5 volts, you'll get tons of current flowing through that. And your standard resistors are only rated at a 1/4 watt. A watt, there's a couple ways to write it. One way is I squared times R. So as your current goes up, the wattage goes up really quickly, and you will light that resistor on fire and it'll smell really bad. So you want this to be, in this lab, I think we'll use 10 kiloohms. Now, that's notation you hopefully encountered in physics. What does the K mean? 1,000. That's the majority of what you'll use for this. You'll occasionally see mega ohms, but most of the time you're between ohms and kiloohms. In that lab, that's all you need to know on that notation. So we're going to be using this type of circuit to build a really simple digital signal. And that's where we have one more symbol that I need to introduce you to. So we usually use little circles to notate terminals, is what we call them. And that's where you can connect things to. Does anybody know what this is?
Diode.
Yeah, it's a diode. Also, LED, light emitting diode, right? It's a light. And so you can hook this up to the digital logic. And there's a trait with these. The current flows this way through them, does not flow back through them. That's why we put this vertical line here to kind of symbolize that it's blocking current, reverse flow current. This needs some amount of voltage to turn on. We call it a turn on, a threshold voltage, VTH usually. That if you put like 0.1 volts on it, it won't turn on. Each color of LED has its own threshold because of the process used to make it. It's about 0.7 volts. But there's a problem here where diodes like to have their own voltage. Like, they like to be whatever that turn-on voltage is. So if this guy wants to be 0.7, and my VCC is 5 volts, there's a problem because this guy might be trying to have 5 volts on one side and 0 volts on the other. At the same time, the device is fighting for only 0.7. So we do what we call a current limiting resistor in series with it, and that stops too much current from flowing through and exploding our light. So in the lab, you will notice that it has exactly that. Logic gates. So, diode, I drew up the inverter before. If you're not worried about what the logic look like, what the transistors look like, this is what's called an inverter. If you put a 1 here, a 0 goes out. If you put a 0, a 1 comes out. Right, that's the same circuit I drew. This is the quick, simple notation for that. I think that's the only gate you need to know for that. We'll get to, or for this lab, we'll get to some other ones because that's kind of the foundations of this course, where we'll have an AND gate. Where C is equal to A and B. Meaning that if A and B are both high, C is 1. Otherwise, C is 0. Similarly, again, I apologize for not being an artist. This one is an OR gate. That just means if A or B is 1, then C is 1. Those are your basic gates. We're going to be working today in our lab exclusively with inverters. So we're going to start with nice and simple. Your inverter is going to drive an LED protected by a series resistor so you don't blow it up. And that's the basic idea of the lab. I'll have you guys read through it this afternoon. Oh, this is awesome. I'm like way ahead of schedule. Sorry, I'm making sure there's nothing else that I want to cover before we get into the lab.
Do we need the breadboards for the lab?
You will need the breadboard. So you're going to have a part that looks like this on there. So it's a little IC, means integrated circuit, that has 6 inverters inside of it. So you're going to place that down in a breadboard. Who here doesn't know what a breadboard is and has never used one? Okay, so a breadboard. I have one of those, fortunately, to show you. This is good. This is actually really good that I have extra.
I don't have mine with me today, so I don't know how I would use the lab.
I have a few that you can borrow. So, this is a breadboard. Now, these are actually kind of confusing when you first get to use them, and I understand that, so I will do my best to explain. The breadboard is broken down into, on the outsides, it has a couple of vertical columns that will have labels above them, like so. They will then be separated by a column, and on the inside, we'll have rows with a little break and then rows. Now, the way they work is you put your power supplies here, so you connect ground to the negative and your power supply to positive. Here I'm pretty sure we're using 9-volt logic, so you'll supply with 9 volts. Lab will tell you for sure. And the way it works is this whole column is connected, and this whole column is connected. So if I have a circuit, and I plug something into here, say the power supply in a battery, then this whole row will have 9 volts. Now each of these rows is connected on half. So that row is connected, that's connected. Connected, connected. Make sense? So then what you do is the ICs, the integrated circuits, are designed to plug into this. So the IC itself will sit here and have little legs that plug into each of these holes. Now, one of these is going to be the positive voltage, and one of these is going to be the negative voltage. I actually don't know which one on this one. It's close enough. And then you're going to have the diodes not the diodes, the inverters inside of it, like so. So then if you need to connect up this diode to that diode, you will have these little guys, which are resistors. They have stripes on them. You will eventually learn what the stripes mean. The stripes tell you what the value of this resistor is. I want y'all to see it. So it's just that little guy. And so you'll take each of these leads, which is what we call the two wires sticking off the end of the resistor. So say that I wanted to connect the output of a diode to ground. Then what I would do, so I'll use this output, is I would plug one end of the resistor into this hole. Well, not that hole because it's taken. I would plug it into an adjacent hole because they're all connected, right? I would put it up, little resistor guy there, and then plug them into any one of these holes in this column. Now I'm going from the output of the diode to the ground. Similarly, I need to power it on, so I'm going to go from an adjacent hole to the positive supply and put it in any one of these holes in the positive column. I need ground connected up there with wires. Now we have a functioning circuit, kind of. We need something that feeds into the input of that diode, but we'll design that too. And so you might have another IC that we build down here somewhere that's plugged in, and it'll have an output that feeds back and hooks up into the input of that diode. Make sense? And then you will know it works because the diode can turn on, the inverter in this case can turn on an LED depending if you're doing it right. So you might do something, let's draw a little bit more interesting circuit. Take the output of the inverter and you put it through a resistor to make sure that you don't break anything, and then put it through an LED, and then connect that to ground. And now, if this is a 0, what's the output? 1, which turns the diode on. So the 1 is high. The lab actually might be an inverted diode, actually, because this is shown connected to the ground. You can do the same thing and connect it to the positive supply, and then a 0 turns it on. So that's the general idea of the lab. It's fairly straightforward. How many of you don't have your breadboard or wire kits? A lot of you. Like 10 of you. I think I only have 8 breadboards.
Does the bookstore keep them on stock?
Yes.
Probably just run down there and grab one.
Okay, so I will end early today. We have another half hour left, but I will end early so that those of you that haven't bought them can go buy them. How many of you have bought them but didn't bring them? Only 2 of you. I can handle that. Okay.
I bought mine, but it's pending.
Pending.
I did it online. And I did it like yesterday, so.
Interesting. I can handle 3. We can figure you out. The hardest part is wire kits. I don't have wire kits. You may have to bum some wires from people.
Okay.
But other than that, you're fine. Because I have breadboards, I will get out the electronic components, and we will make this work. Because I really do want to get you guys at least a couple of times in the lab, so I'm there to help you before the world explodes and we go online. This is a lot harder to learn by yourself than it is in person.
So do you need bags here, or?
It'll be at the 128, which is just across the hall. Oh, is this 128? That's 127? Okay.
Yeah.
Sorry, I've been dyslexic with those 2 numbers since I got here. So, yeah, it's across the hall. That's it. Oh, shoot. It has that one. Your wild card should hopefully be able to swipe you into that lab. There's a card reader next to it. Your card should be automatically set up if you're registered for this class to swipe you in. If somebody could just walk over there and see if it works, that'll be helpful. I'll go with you. Anyways, any other questions before I send you off to an early lunch? Excellent. Cool. Thanks for coming, guys. Sorry, I need to speak a little louder. Okay, I mean, that's fine. We can let you in.
Yeah.
Eventually you want it because you can use lab time on your own as long as no one else.
Do you know in the library? Some nights, and I have no idea where to do.
Oh, I don't know. Like, I'm a first semester professor, and my whole life has been trying to catch up to the COVID apocalypse, so I'm a little bit out
How
of it.
needs to happen over
Susan should be up at her desk
Yeah,
in
well,
the
we'll
ECE
see
office,
you,
and just
last-
straight up these stairs,
Okay.
and she will probably have answers for you.
Okay, thank you.
Yeah.
Sorry, so can the breadboard and wire kit both be bought at the bookstore?
Yes, it should all come as one kit.
Okay, you don't have to order online first, you still.
If you do, things have screwed up. You really shouldn't need to.
So I work in Salt Lake.
Okay.
And on Wednesdays, like that's the other instructional day.
Yes.
Would I be able to just watch the video on Wednesdays?
Yes. No. That is okay. I'm gonna actually stop recording right now. The audio at the moment is my biggest concern. It is a little suspect.
Okay.
I'm trying to talk loud so it can hear me, but I have a lecture right before this, and then this one, I feel like I'm running out of voice already. So, yes, you can watch the videos. I will try to make them reasonable. If we go fully online, it will switch from an hour-and-a-half lecture to like series of mini videos, probably, which will be smoother.
Yeah.
But I like face-to-face because I think it's better.
Right. I'll try to still come on Mondays.
Yeah. Yeah, no, we're going to be very accommodating this semester.
So at least 3 of us tried to get into the lab and it didn't work.
It doesn't work. Okay, I will find out what we need to make that happen. For now, I can get people in.